Hi everyone. So this example is also for torque. So example number 2 for torque, but here is kind of like the torque revisited type of example. So this is kind of revisited in chapter 11, but it's the same exact thing. It's just torque as a cross product. And here, when we revisit torque in chapter 11, really what we're talking about is saying that like we can measure the torque of any point. So it doesn't have to be like a continuous body that is rotating. It can be just a point, and we can measure the torque of that object about any axis of rotation or any point. Here, the point is the origin. That object, that point, doesn't even have to be rotating about the axis or just the reference point. So here we have our axis of rotation. I put that in quotes because we don't know if we're actually even rotating about that axis. It's just kind of a reference point here. And point A is the thing that we're measuring the torque about that point. O here. So O obviously is at the origin. So we have in this figure 11-11A, three forces, each of magnitude 2 newtons, acts on a particle. The particle is in the xz plane at point A, given by position vector r, where r is equal to 3 meters, and the angle that they give us right there is 30 degrees. What is the torque about the origin O due to each force? So we just want to find 3 separate torques due to 3 separate forces. So let's start with force 1 here. And the first thing we need to do, we know the force, we know the R. So all we need to do here is find the angle between our R vector, and our force vector. So that's this angle right here. Oops. This angle right here. Okay, so if we look at those those triangles that are made by all of these different lines that we have, we can see that this line right here is parallel to this line right here. And then this line kind of bisects, that R vector bisects those two lines, which means that the angle between F1 and R is also equal to 30 degrees. So that makes it a little bit easier for us. So all we're going to do here is find the torque from that force 1. So we get torque from force 1 will be equal to R F1 sine, and again we found that angle to be 30 degrees. And so now we can just plug in our numbers here. So torque 1 is equal to R, which was 3 meters, and it's the same for each one of those torques. Times F1, which is 2 newtons, and again that's the same for each one of the 3 torques. And then we get sine of 30 degrees. So here, torque 1, the magnitude of that, we get 3 times 2 times sine of 30, which ends up being, of course, 3. And that's newtons per meter for our unit for torque 1. All right. If we want to find the direction of that torque, we then use our right-hand rule, and it's going to look weird probably in the video, but what we do, we know that this is the YZ axis, and X is coming out at you from the page, which is kind of weird, but we point our fingers in the direction of the R vector, we curl our fingers in the direction of that force 1 vector, and we can see that our thumb is pointed, so it's opposite in the video. Our thumb is pointed in the direction of this F3 vector. So we can see that this is going to be the direction of torque 1, would be that F3 vector there. Okay, I'm not going to leave that on the picture, but just a note about direction there. Okay, so let's look at torque from force 2. Force 2 is directed straight downward in the negative z direction in this picture. So what we need to do here is, again, first we have to find that angle between our F2 vector and our R vector. So that's going to be this angle right here. And if you can see, that's the top angle in this right triangle here. 3 dimensions is very difficult to draw in 2 dimensions, but you can kind of see that that triangle is coming out at you there. So that means that this angle is going to be 60 degrees because we know that the angle on the other corner of that triangle corner of the triangle, yes, that makes sense, is 30 degrees, and then this is a 90-degree angle right there. So because of all that, that angle is going to be 60 degrees, and so we're going to plug that in now. We get torque 2 equals RF2 sine of 60. And so plugging in our numbers, we get torque 2 is equal to R, 3 meters, F2, 2 newtons, times the sine of 60 degrees. Again, I didn't say this for the first one, but make sure that you are in degrees when you're doing this problem. Again, this unit is very difficult because you kind of have to switch back and forth between radians and degrees. So we get 3 times 2 times the sine of 60. And that ends up being 5.2, just about 5.2 newtons per meter. If we want to know the direction of that torque, again, we point our fingers in the direction of the R vector, we curl our fingers in the direction of the F2 vector, and then our thumb actually points in the opposite direction of that F3. So this would be our direction of torque 2. Okay, that would be the positive y-axis. I should just write that down next to these. So direction would be negative y here, direction. And then this would be positive y, direction. Okay. All right. So last but not least, we want to find torque 3. So torque 3 is going to be our F3 sine, and then we have to find that angle. Now, we want to find the angle between F3 and the R vector. Now, this is a little hard. It's hard to see just because, you know, it's hard to draw in 3 dimensions when we're only in 2 dimensions. But remember that R vector is kind of coming out at you like this. F3 is going in the direction just straight left. In this picture, in my video, I'm sorry, it looks like this. It's going this way. So since we have R coming out at you, F3 going straight left, if we look at the angle between those two, it's going to be 90 degrees. It's really hard to see that in this picture, but that angle between F3 and R is 90 degrees. So I'm going to write that here. Of course, we know that the sine of 90 degrees is just 1. So we get torque 3 is equal to 3 meters times 2 newtons times the sine of 90. So we get torque 3 is equal to 6 newtons times meters. And then here, that direction is a little bit more difficult. We're going to point our fingers in the direction of R and then curl our fingers in the direction of F3. And we can see that torque is going to be kind of down at an angle. And that's going to be it's really hard to draw, down at an angle like this. In positive x, negative z plane. All right, so those are our 3 different torques caused by those 3 different forces.